Alright, so these are the two four-membrane extension notes. Here are the four assessment statements that are going to be covered in this video. And again, this should be used in addition and after you've done your own reading notes. And all I'm trying to do is fill in a couple of details that maybe you don't have, or make some connections for you that may be a little difficult to make since you took biology 2 or 3 years ago in 9th grade. Alright, so let's go ahead and move on. Jot those down if you don't have them, but make sure that in your notes you are telling me what these words that I'm underlining mean according to IB. You need to tell me what draw means, what label means, explain, list, and define, okay? Alright, so let's go ahead and move on. While you do that, go ahead and pause, and we'll catch up. Alright, so the first section, 2.4.1, is about drawing and labeling a diagram of the structure of a membrane. And really what I'm going to draw is a two-dimensional model. The one in the book is three-dimensional. This is just going to be like a cross-section. So know that there are more of these phospholipid heads behind. I apologize for my poor artistic ability here. But these phospholipid heads have phospholipid tails that all point towards the middle. Okay, and when I mean the middle, I'm talking about pointing to each other, and really explaining why that happens is going to be our next target when we talk about hydrophobic and hydrophilic parts. But these this is a phospholipid bilayer. I guess I can label that for you. I'll label it on this side. This is my phospholipid, sorry about that, can't spell either. This is the phospholipid bilayer. It's made out of phospholipids. There are two of them, and it's a layer. So we can have monolayers as well, and I would urge you to ask me about that in class. But in our cell membranes we see a phospholipid bilayer. And so each one of these, and you can label it, is a phospholipid. But we've also got a couple of things that are also in this phospholipid bilayer. We also have, this is going to be a terrible drawing, but we've got a protein as well that can be embedded in the middle of this phospholipid bilayer. And really this protein can take on several different roles, which we'll talk about in a few minutes. We'll call this one, we'll label this one an integral protein. And really what this is allowing, what it allows for is things to move in and out of the cell. And usually they're pretty specific about what kind of molecule comes through, because it does have its own chemistry. It is a protein, it is made out of amino acids, and there are some amino acids that carry charges, and there are groups, or they're variable groups, which is what makes each amino acid different from each other. Also embedded in, I'm just going to label, I guess I'm going to put this on top of this because I don't want to extend this drawing too much. We have some, let's just draw it right on top here. We have some things that have this protein, and then we've got some carbohydrates that come off of it, and these are called glycoproteins. And they are basically used to help in communication and in recognizing other cells. So this refers back to the bacteria video that we watched during SEOC seminar, or will watch if you're in period 8 and watch this before SEOC seminar. And then we have also embedded in here, let's say, we're just using color yellow because that's the color that was used in the book. We have some cholesterol. And what cholesterol is used for is to add stability to this model. Because this model, it actually has a name called the fluid mosaic model. You might remember that from Bio 1. I hope you do. Fluid means that it moves. Mosaic means it's made out of lots of different pieces, like in art, that's what mosaic means in art class. And so what this model explains is that even though it looks like these proteins and glycoproteins and cholesterol and phospholipids are pretty static, they're actually all moving around, and these glycoproteins are kind of floating around. These proteins can be moving around, but it's the cholesterol that gives it a little bit of structure, but it's also the chemistry of the phospholipid bilayer. So that's what we're getting ready to talk about, and that's going to be 2.4.2. So we've got our I'm just going to draw this a little bit larger. We've got our phospholipid head, and we've got our phospholipid tails. This is one of those. Okay, so if we're looking at one of these, we know that we've got, if we remember back, we've got what this is equal to is 1 glycerol plus 1 phosphate group plus 2 fatty acids. So really what that drawing looks like, this is just a rough sketch. We've got a 3-carbon glycerol off of one of these carbons. Well, remember we've got some H's here as well, but we've got our phosphate group. And this is really what carries the negative charge that makes this end of it polar, because it's got a negative charge. Okay? And then on these other 2 carbons, we get our fatty acid tails, which I'm just going to draw in a short chain that's not quite typical of, I mean, it's just to represent our fatty acid tails. I'm going to throw in a double bond here. We know we've got our hydrogens all the way around, because each carbon has to have, you remember, 4 bonds. So this one's already got 1, 2, 3. It only needs one. It can only take 1 more hydrogen. This one's got 1, 2, 3. It can only take 1 hydrogen, and this one can take 3 hydrogens. So this is saturated. Unsaturated, because it's got a double bond. It's unsaturated fatty acid. But this is really the key, because there are 2 parts to this this phospholipid. This phosphate head is the polar component, and these 2 fatty acids are nonpolar. And that really means that these electrons are pretty stable in this section, and this phosphate group has a negative charge, which means that it can create hydrogen bonds. With water. Remember, water is polar. It's got negative and positive ends because of the unequal electron sharing between oxygens and hydrogens. So the polar phospholipid head, or this blue circle here, really can bond with water, and that's really why we have them on the outside of the cell membrane. And just to give you some context, going back to our first diagram, let's assume that above the drawing is the outside of the cell, and underneath it is the inside. So really in this watery environment, remember 70% of our cells are made out of water, there's a little barrier in here because the nonpolar part, the hydrophobic component that's not going to bond with water, remember phospholipids are lipids, therefore hydrophobic, these nonpolar fatty acids are not going to bond with water because they're protected here in the middle. But they're not actually bonding to each other because there is no charge in this molecule, at least in the fatty acid component, so they're not creating a bond, therefore able to move across each other, leading to this fluid mosaic model idea. But it's cholesterol and the chemistry of the polar part that's staying on the outside of the cell, outside of the cell membrane, or inside the cell membrane, to bond with the external water. I hope that makes sense, and if it doesn't, write down some questions and we'll talk about it. Alright, so 2.4.3 has to do with those membrane proteins. And what we need to do is be able to list the functions of these proteins. And we need to be able to, it doesn't tell us how many, so let me give you several of them. You should know all of these. So the first one is that these membrane proteins can serve as hormone binding sites. So think back to the bacteria talk that we watched. Sometimes they're called hormone receptors. Basically what they're doing is receiving signals from the environment from hormones. And a good example of this would be insulin. Remember, insulin regulates blood sugar, so it allows for some signal reception of what the environment is and what's in the blood system. Secondly, they're immobilized enzymes. With the active site on the outside of the cell. Okay? But basically what they're doing is stationary inside the cell. They're not just floating around, and if the substrate of the enzyme touches or fits into the active site, the enzyme will work. And a good place that we find these would be in the small intestine. Remember, the small intestine is where a lot of absorption of macromolecules or carbs, lipids, and proteins happen. And so the enzymes are at work there in the small intestine, really where absorption and digestion, the end of digestion occurs. There's also cell adhesion. Remember, adhesion is basically sticking together to form tight junctions or tight connections, but sometimes we see the word junction in biology between groups of cells in tissues and organs. So essentially it's basically kind of like glue that's sticking cells together, and you can think of this in any kind of organ or tissue. So I'm not going to write an example because it's pertinent everywhere. There's also cell-to-cell communication. So essentially, this relates a little bit more to the bacteria talk that we talked about, that we watched, excuse me. But another example would be neurotransmitters, or chemicals that are used to send signals from nerve to nerve, neurotransmitter in nerve cells. And we'll learn more about that a little later in the year, near the end, right before the test, before the IB exam. And other times, proteins can be used as channels for passive transport, which we'll talk about in just a second. we call them pumps, but basically they're channels, but not for passive transport, but for active transport. Alright, so we're going to talk about this one right now. Or we're building up to it, excuse me. Alright, so 2.4.4, so I guess before we talk about diffusion and osmosis, you should, just to recall, that these are both about transporting things across the membrane, across the cell membrane. So to get things in and out of the cell, and there are two ways that we do that. The first that we're going to talk about is passive transport, and then there's active transport. And so there are three kinds of passive transport that we're going to talk about: diffusion, osmosis, and facilitated diffusion. So let's go get started and talk about diffusion first. Before that, you should recognize that in passive transport, really what we're talking about is no energy is used, and really what's happening is that there is movement from high concentration to low concentration. That's really what we're talking about, but it depends on what we're referring to. So let's define diffusion first and move from there. So diffusion is defined as the passive transport. Remember, this is, so no energy is used. Is expended here, but the passive transport or movement of particles from a region of high concentration to a region of low concentration. Now, let me just point out, this doesn't have to happen across the cell membrane, but that's really what we're focusing on or building up to. So it can just be a molecule spreading out in an environment. But what I want you to recognize is that this is about particles, as opposed to osmosis, which is essentially the same thing, but instead of particles, we focus on water molecules. So just to give you an example, let's say we've got, oh, that's not a, let me redraw that. So let's say we've got a beaker, and we have put in an impermeable membrane. So an impermeable membrane, sorry, let's say it's semi-permeable. And we've got some water in it, and we've got lots of salt on one side, neon green salt. But the salt cannot pass through the semi-permeable membrane. Water can. So really what's going to happen is that water is going to move over here, because on this side we have a high, if we look at the solute concentration, it's obviously higher on this side than this side. But that means that inversely, if there's not a lot of solute here, we've got a higher water concentration and a lower water concentration on this side. But because what would normally happen in diffusion is that the salt would move across. But I told you that salt can't move across this membrane. So instead, because water can, water is going to move from its high concentration to its low concentration, which happens to be low solute concentration to a high solute concentration. But remember, osmosis is about the water, and really that's what we're focusing in on. But the whole point of these processes is to reach dynamic equilibrium. Equilibrium meaning equal, and dynamic meaning that it can change because molecules are still moving back and forth. The water molecules are moving back and forth across the semipermeable membrane. And the reason these molecules will move across is because molecules are always moving. Even the chair that you might be sitting in right now, the molecules in it are moving. They're not stable unless they were at 0 Kelvin. They're moving. So they're bumping into each other and they're trying to spread out. And so really what they're trying to do is reach dynamic equilibrium. Okay? So we're going to stop there. I think I've gone on long enough.